Hello everyone, my name is Ardnt and I am going to teach you about a topic in chemistry, right? So the topic is name reactions. We know that there are many reactions in chemistry, but it is not necessary that all the reactions have a name, right? But in name reactions, there is a specific name attached to the reaction. So let's see what are name reactions, right? So name reactions Name reactions are the reactions which have specific name attached to the reaction, and this name is given by the scientists who have founded it, right? So I am going to teach you about a name reaction, and this name is Ardent Eistert reaction. What is the name? Ardent Eistert reaction. Okay. So name of the reaction is Ardent Eistert reaction. So first of all, we will see the basic reaction. What is the starting material involving what are the reagents and what is the final product we obtain. So basically Ardent Eistert reaction is a three-step reaction. Okay, the starting material of the reaction is a carboxylic acid, right? We know that COOH group represents a carboxylic acid group. In the first step, the reagent used is ionic chloride. We can also use phosphorus trichloride or phosphorus pentachloride. Any of the three reagents can be used to give acyl chloride, right? We obtain acyl chloride as a product of first step. In the second step, we use diazomethane. Diazomethane is a very reactive molecule, right? So this molecule react with acyl chloride to give us another compound, and the compound is like that. This is diazo compound which also has an acyl moiety, right? So this compound will also react with another reagent in the third step to give us a carboxylic acid. And what will be the reagent we will use? It is silver oxide or light. H nu means it could be sunlight or it could be UV light. Basically it is light, and we are using water as a solvent here, right? So we will obtain a carboxylic acid. So basically we can see here that we are obtaining carboxylic acid molecule as a final product, and the starting material is also a carboxylic acid. So what is the difference? The difference is this CH2 group, right? Basically we are adding CH2 in between R means an alkyl chain and COOH group. So it can also be called a homologation reaction. A homologation reaction. So what does homologation stand for? It is generally an addition of a carbon atom to any alkyl chain, right? Here R can be any alkyl group or aryl group. So we can say that Ardent Eistert reaction is a homologation reaction of any carboxylic acid molecule. So this is the reaction which involves three steps and three different reagents, right? The final product will be carboxylic acid molecule. So now we will see the detailed mechanism of all three steps one by one. So in step 1, we know that the starting material is carboxylic acid. We can write it as that, right? Now, what are the reagents we are using in the first step? It is thionyl chloride. What is the name? Thionyl chloride. Note that the word thio stands for that sulfur atom, right? So whenever you see sulfur atom, you can use word thio, or the vice versa. Whenever you see word thio, it suggests the presence of sulfur atom, right? So this compound is called thionyl chloride. But there are some other reagents also present which we can be used here. So I am writing it, or we can use either sulfonyl chloride or phosphorus trichloride or phosphorus pentachloride. Okay. So basically any of the three reagents can give us the product as acyl chloride. How will we write acyl chloride? This is our acyl chloride, right? So we can see that the OH group has been substituted by a chloro group. Which group? Chloro group, right? So we can say it is a simple substitution reaction, right? But the reagent we use is either thionyl chloride or phosphorus trichloride or phosphorus pentachloride. In this step of the mechanism, we will not show you the detailed mechanism because it is a bit concerted mechanism, right? So we can say that it is a substitution reaction, and OH group of carboxylic acid gets substituted by a chlorine atom, right? And what we will get? An acyl chloride, okay? So now we will see second step. Now, at the end of first step, we obtain an acyl chloride, right? Now in the second step, we will react it with diazomethane molecule. Now, the molecule diazomethane does not have a simple structure. Actually, it can be shown by two different structures which are in resonance with each other, okay? So first of all, we will see what is the structure look like of this diazomethane molecule. Because then only we will be able to know that how it will react with this acyl chloride molecule, okay? So I am first of all drawing the structure of this diazomethane molecule, and then we will talk about the mechanism of this reaction. There are two nitrogen atoms and one CH2 group, right? So this is the structure of diazomethane molecule. Here we can see that there are two double bonds attached to a particular nitrogen atom. So this nitrogen atom is having 4 bonds in total, right? But we know that in organic chemistry, a nitrogen atom can only form 3 bonds. And if it is forming 4 bonds, then we need to add a positive charge on that nitrogen atom. That means that nitrogen atom has consumed its lone pair in that formation of bond. Okay, so it is positively charged. Now, the terminal nitrogen atom is having a negative charge. That means it is having an extra lone pair of electrons, right? Now this molecule has two structures. It can show resonance and it can also show another structure, right? And that is by the help of a resonance. So how it will happen? This negative charge will get shifted to this bond. So the double bond will get converted to triple bond, right? and this negative charge will now get converted into this bond. So this nitrogen atom will now be totally neutral. And this nitrogen atom will now have 5 bonds if these two double bonds also remain there. But this cannot happen, right? So this bond will now get broken and the charge will sit on this carbon. So what will happen? There will be a negative charge on this carbon atom. So these are the two structures that are responsible for the diazomethane structure, right? So here we can see that there is a negative charge on this carbon atom. So this compound is more reactive in context of this reaction, and this negatively charged carbon will react with this compound. So let's see how it will react. Okay. So I am drawing the same structure that we drew for here, which was having a negative charge on carbon atom. This is a structure, right? So we can see that the negatively charged carbon atom has electron density, high electron density on its shell. So it will attack on a carbon or any atom that has electrically positive, right? So we know that a carbonyl carbon is a partially positively charged, right? So this negatively charged carbon will now attack on that carbon, and this double bond will be broken, right? So what will we obtain? We will obtain a negative charge on this oxygen. The chlorine group will already be there, and a new bond between this carbon atom and this carbon atom will be formed, and that is this bond, right? We will obtain this compound. This is the compound we obtain. Now we can see that this chlorine atom is bonded with this carbonyl atom, right? Now the negatively charged oxygen atom is not stable. It will try to form a double bond with this carbon. So this carbon will break a bond with this chlorine atom, and what we will obtain? We will lose a chlorine atom from this molecule, and we will obtain a new compound which will be like this. Right? The new compound that we will obtain will be like this. Okay? So now we have seen that a chlorine atom has already been removed from this compound, but this will not be as it is. Actually, it will be combined with a hydrogen atom. So where will it find a hydrogen atom? Right from here. Okay. So this chlorine atom will react with this hydrogen atom. How? Let's see. The negatively charged chlorine atom will attack on this hydrogen atom, and the electrons of this bond will get shifted over this carbon atom, right? So what you will obtain? We will obtain carbon ion. Right? Whenever we see a negative charge on a carbon atom, it is called a carbon ion. Okay? So this is the compound we obtain at the end of step 2 of the reaction. There is still step 3 of the reaction is remaining, and we will see it in the next step. Right? So this is the compound we have obtained at the end of step 2 of the reaction. We will write it over here. Now we will see step 3, right? this is the compound that we obtain at the end of step 2. Okay. So we have seen earlier that in the step 3 we are using silver oxide as a reagent. Silver oxide or light, both can be used as a reagent, right? So what will this lead to? Silver oxide or light can lead to free radical reactions. So here we can see that two nitrogen atoms are present in the structure in the terminal part of a compound, right? At the terminus they are located. So whenever two nitrogen atoms are there at the terminal of the compound, it can be set free in the form of nitrogen gas. Okay, so here they will leave the molecule and give nitrogen gas. So I'll show you the mechanism of this of the removal of nitrogen gas. So we can see that this pair of electrons will be donated to this nitrogen. Okay, and that will give this compound. And the nitrogen gas, which we can also show by this way, is removed from this compound. And what we will obtain? We will obtain this compound. What is this called? This is a carbene. What is called? It is a carbene. We might not have seen this intermediate earlier in our studies, but this is called carbene. Why it is called? Now we have seen that carbon atom has a valency of 4 and it can form 4 bonds with other atoms, right? But here we can see that this particular carbon atom has formed only 2 bonds. The one bond is with this carbon and another bond is with this hydrogen atom. So it has formed only 2 bonds and that's why it is called a carbene intermediate. Now remember that carbene is a very reactive intermediate and it can give various rearrangements as well, rearrangement reactions as well, right? So it will also give a rearrangement reaction here. So how will it fit there? It will undergo a rearrangement. So first of all, this negatively charged carbon will donate its electron density to its vicinal bond. So this single bond will now be converted into a double bond. So we can write this as, so this structure will remain as same as here. The single bond will now be converted into a double bond. So we can write this as this, right? The negative charge has now become a double bond, a pi bond, right? And this bond will now break. This bond will be broken and this group will now get attached to this carbon. So we can write it as this, right? This R group has rearranged from this carbon to this carbon. It has broken the bond with this carbon and will form the bond with this carbon here, right? So R group has now attached to this carbon instead of this carbon. So what we obtained? This molecule. We can also write this molecule as this way, right? I have just written the oxygen in the same line, okay? So this is an intermediate molecule. We can call it a ketene. Now, why we call it a ketene? Because it has a structure like a ketone. How is the ketone structure? Carbon double bond oxygen, okay? It also has a double bonded 2 carbon atoms, means it has a structure like ethyne, like ethene, okay? So a combination of ethene and ketone makes a ketene intermediate. So in step 3 what we obtain is a ketene intermediate, right? Now, this ketene intermediate can react with different types of solvents to give different end products. Here, we have written that we are using water as a solvent, right? So it will give product accordingly. The final product is not yet ketene. Ketene will still react with the solvent to give final product. So we will see how the final product is obtained from a ketene, right? So we will write the structure of ketene. This is the structure of ketene. This is the ketene, right? And the solvent we have used is water. We can write the structure of water as this, right? Two hydrogen atoms are bonded with an oxygen atom. So how it will react? We know that oxygen has two lone pairs in its solution, in its uh, atomic orbital, right? So oxygen is also an electronegative atom. So what will it do? It will attack on an electropositive carbon atom. We know that a carbon atom that is doubly bonded to an oxygen atom is partially electropositive. So this atom will attack on this carbon and this double bond or this double bond. One of the double bond can be broken, right? So which double bond will be broken? The double bond that is more strong will not get broken and the bond that is less strong will get broken. So here the attraction between carbon and oxygen will be more because it will be more polar bond. And this, the double bond between these two carbons will be a bit less stable, right? So it will get broken and we can obtain a negative charge over here. So what we will basically obtain? This carbon atom is now forming bond with this oxygen. So we can write it, the water molecule as here, right? Oxygen is forming three bonds here, so it will also have a positive charge, right? The double bond has now become a single bond. The negative charge is there on the carbon and the alkyl group and hydrogen is there only. So what will happen now? This molecule will now try to get stabilized. So how it will get stabilized? This negatively charged carbon atom will attack on the vicinal hydrogen atom, right? The vicinal hydrogen atom, it is not possibly the vicinal, but the hydrogen atom is in vicinity of that carbon atom. So this will attack on this hydrogen atom and the electrons on this of this particular bond will get shifted to this oxygen atom. So what we will basically obtain is this compound, right? So what is this compound? It is same as RCH2 C double bond O OH. This is the carboxylic acid. Isn't it? This is a carboxylic acid and this is the final product of our reaction, right? But note that here we are using water as a solvent and that's why we are obtaining carboxylic acid as a final product. But there are some other solvents as well by which we can use different products, by which we can obtain different products. So let's see how many different products can be obtained by using different solvents. We knew that ketene was the intermediate, right? Ketene was the intermediate and now we can use different solvents. The one we have already used, water, and what we obtain as a final product? a carboxylic acid, right? Another solvent we can use is ammonia. We can also use ammonia as a solvent. And in case of the use of ammonia, the product we obtain is an amide. Okay? So OH group from water is now connecting to this carbonyl group, and we are obtaining a carboxylic acid group. Here NH2 portion will get connected to this a carbonyl group, and we will obtain an amide, right? The third solvent that we can use is methanol. We can also use methanol in this reaction. The product we will obtain is an ester. This is an ester, right? But in this case, we are using methanol as a solvent. Another solvent we can use is methylamine, right? We can also use methylamine as a solvent, and that will yield substitution amines. So in this way, we can see that different products are obtained depending upon the different solvent molecule used. But the majority depends upon this intermediate, this reactive intermediate, which is known as ketene. Right? So this is the main reactive intermediate used in this reaction, and we get these many final products in the reaction. Okay? So this is all for the Ardnt Eistert reaction.